All right, let's look at this a lot more closely, and specifically we're going to look at the concept of a fictional force. And what happens is, due to a rotating reference frame, we get an acceleration component that appears to be a force from an object in the rotating frame. So, I'll draw a rotation here, and I'll give it a radius. Now, if I am a particle that is on something rotating, let's say, for right now, we'll use a record player or some turntable. It's rotating this way. And so this particle has uniform circular motion in this direction. It's moving at so many, well, let's use a record player, 33 1/3 rotations per minute. And so an object on here will, due to frictional forces, move. And as the velocity gets constant for this object, the only frictional forces are in the direction of the center, because they provide the turning force. What the object feels like is happening, because sees its local environment as being unmoving, is that its inertial component wants to go this way. It wants to move in a straight line. So as it starts moving and it's turning, it has an inertial component that feels like a force. Right? And this is called centrifugal force, which is force away from the center. And most of the literature will say this is not a force. It is a fictional force, and it's solely due to the particle being in a rotating frame. And so let's take a record player and let's flatten it. And we can put a penny on it. So we have a penny sitting on a record player. And we'll put that penny R away from the center. And so this is now rotating, but from the penny's point of view, it's sitting still. And it has a turning force provided by friction, and it has an outward centrifugal force that is really the inertial component. And so we can look at this penny as not moving. And so it has a normal force and an mg. And so we know that it's rotating at, well, let's turn this into a pure problem. So record players go at 33 1/3 rotations per minute, but let's just make it rotating at some angular velocity. It has some angular velocity that it's moving at. And so what we want to be able to do is to find how these all balance. And in the previous lecture, and in chapter 10, we talk about how the radius times the angular velocity gives us the tangential velocity. And so that's going to be our translational unit here. We're going to look at this force diagram, and we're going to build some components out of it. So first we're going to look at the sum of the forces in the y direction. And n minus mg equals 0, or the normal force is equal to the mass times the acceleration due to gravity. And so we have the normal component of the penny on the record player. And then we're going to look at, I'm going to call this the sum of the radial components, and we're going to talk about the fictional force minus the frictional force, and they're going to need to be equal. So f of n needs to equal f mu, and f mu. And the fictional force is supplying the turning force, or this is supplying the turning force. This is what's turning it. So that is the inertial component, And if we think back of our previous example with the banked turn, that's going to be supplying mv squared over r. So we have a series of balanced forces that are acting upon our penny. And we have the turning force being supplied by the friction. And let's flip these around here, my bad. The friction penny, no, the penny does want to slide out. I have that right. Sorry, I want to rewrite that, sorry. And so the turning force is supplied by that. Turning force balances out the inertia. But what is friction? Well, that's the normal times the coefficient of friction. And so we have this equivalence here, that the penny is going to take whatever the coefficient of friction is, the masses will cancel out, and let's put this in terms of r. But right now, it's the velocity component I want to look at. Because we can talk about how many rotations we have in time, or we can talk about an angular velocity, we're going to use this translational tool here to change this. So we get we get g mu equals r omega squared over r. So g mu equals r squared omega squared over r, or g mu over omega squared equals r. And so we can find the radius to set an object if we know the coefficient of friction, given its rotational velocity, the coefficient of friction, and the gravitational system it's in. And so let's double check this unit-wise. Right? Gravity, or the gravity acceleration is meters per second squared. Omega is seconds squared, and mu is unitless. So second squareds cancel second squareds, I get units in meters, and r will be in meters. So this works for us. And we have the ability to measure where to position something on a spinning surface if we know the coefficient of friction. And it's a common problem you'll see sometimes is, put a penny on a turntable. I've had ants with their coefficient walking across cake pans, I think I've seen. But the idea is if you have something turning, you're going to want to slide out because that's your inertia. That's counteracted by the friction turning you inwards. And that acceleration inwards that the friction is supplying is our uniform circular motion.